But like Thompson's scenic railway, it relies on a mixture of momentum and gravity to turn potential energy into kinetic energy. A ride of this scale, however, means rewriting the roller coaster rules. And today, Michael has the park to himself to put the ride through its paces.
The Millau Viaduct, soaring high above the French countryside. It's the world's tallest bridge. To support this engineering marvel, its designers had to construct 7 of the tallest bridge piers on Earth.
All the piers represent something like 90,000 cubic meter or more than 200,000 tons of concrete. And this is a concrete which is of a very high strength.
Chief engineer Michel Villajeur had just 4 years to finish the bridge, or face fines of up to $30,000 per day. So to save time, each pier was built simultaneously at 7 individual work sites.
From here we can see the shapes of the piers. They look very simple, but it's very far from it.
Due to the uneven valley floor, each pier is constructed at a different height. The tallest, a record-breaking 804 feet. Their octagonal shape tapers gradually, splitting around 300 feet below deck height for added flexibility.
It was necessary that the architect worked to make nice piers, but at the same time, it was necessary to select shapes which could be erected with self-climbing forms.
Engineers built each pier in 13-foot sections, using a self-climbing frame. A hydraulic-driven system pushed the giant concrete mold up in stages.
One of the big problems, of course, was to lift concrete, because this pier, this one, is 245 meters high.
Cranes lift buckets of concrete, which is then poured into the concrete mold. After each pour is set, the mold is dismantled. The frame carrying the mold is then mechanically pushed by the hydraulic jacks up the piers and re-anchored in the set concrete. The mold is then reassembled for the next pour. Each cycle takes about 3 days.
You can see the lines between the different lifts, concrete lifts, and also the traces of the elements where the climbing forms could be anchored to the concrete.
The piers are completed ahead of schedule, in just over 2 years.
Developing solutions to erect the 7 piers in the same time, it was a very, very, very big adventure.
With the bridge piers complete, Michel is ready to tackle his next challenge: construct Milau's 1.5-mile-long bridge deck, long enough to span the vast Tarn Valley. The staggering height of the bridge presents a unique challenge for Chief Engineer Michel Villajeur.
The great enemy of the design of the bridge is the wind. The deck is about 150 meters above the Plateau de France, and so this means that we have rather high winds.
How do you make the world's tallest bridge stable enough to handle the hurricane-force winds high above the town of Millau?
The solution is to reduce the wind force.
Protecting the Millau Viaduct's bridge deck from high winds would be impossible without an ingenious innovation made by a civil engineer a half-century ago. Professor Luke Bisbee is exploring one of Britain's most iconic bridges.
All right, now this is what I'm talking about. A vertigo-inducing 135 meters below me, lies the Severn Bridge.
The Severn Bridge provides a vital link between England and South Wales.
The main section of the bridge is over 1,598 meters long, which at the time made it the longest bridge in the world. I can actually see through this hole about 1,000 meters down the bridge. It's absolutely incredible.
The length of the bridge is impressive, but its ability to resist the high winds that frequent the River Severn is what makes this structure revolutionary. Lying inland from the Atlantic Ocean, the River Severn begins where the Bristol Channel ends. The high ground of Exmoor on the south shore and the mountains of Wales on the north create a funnel for the prevailing westerly winds and Atlantic storms, increasing their power.
Building a bridge that could withstand severe winds was really essential. And even on a relatively calm day, standing here underneath the bridge, you really get a sense of the wind that they were up against.
Civil engineer Sir Gilbert Roberts was tasked with building a bridge across the River Severn. Sir Gilbert Roberts broke his original truss lattice design while testing it in a wind tunnel. As he waited for a replacement model, he researched the aerodynamics of other objects, leading him to a truly groundbreaking idea.
So what I have here is a model airplane, and you can imagine that the wing of this airplane is representing the bridge deck. So a wing has a curved surface on the top, and it has a flat surface on the bottom, and this means that air passing over the wing has to travel further across the top than on the bottom.
As air passes over the curved surface, it speeds up and loses pressure. The pressure of the air below remains high and pushes up towards the low pressure area, creating lift.
What I'm going to attempt to show you is with this hairdryer to generate some wind, the force of the little model airplane will decrease, and that decrease will signify the lift force that we've generated on the model. So there we have our starting weight, 45 grams. Right, so there we go. The engineers here didn't want that to happen to the bridge deck.
When Luke flips the airplane over, the lift effect is reversed, creating a downward force.
What we should see is that this force should increase rather than decrease. You can actually see the downward force that's coming from the wind. That holds everything nice and taut and safe in very strong winds.
Now that the curved surface is underneath, air loses pressure as it speeds up, and the high pressure above presses down.
And of course, this is exactly the principle that the engineers used on the Severn Bridge.
Sir Gilbert Roberts and his team created an aerodynamic steel box girder deck, the first of its kind in the world. Hollow and only 10 feet deep, the shape of the deck creates a wind flow that holds it firmly in place. Over the years, 13 vehicles have blown over while crossing the Severn Bridge. But the bridge itself has always held on strong.
Although this beautiful bridge has passed on the burden of heavy traffic to its younger brother just downstream, it's still managed to carry more than 300 million vehicles since it was first constructed in 1966. And thanks to Sir Gilbert Roberts and his team, it's set to do so for many more years to come.
Soaring over 2,000 feet, the Tokyo Skytree is the tallest freestanding tower on the planet.
It is the world's tallest tower in one of the world's busiest cities. So it was very challenging work for us to construct.
More than 6 times higher than London's Big Ben and twice the height of its predecessor, the Tokyo Tower, Skytree is changing the face of Japan's capital. But as high-rise architect David Malott reveals, building to this height in this highly congested city poses a unique challenge.
The engineers at Tokyo Skytree had to put a tower that's twice as high as Tokyo Tower on a piece of land that's only a quarter of that size.
The proportions of a super tall tower are crucial. If a structure is more than 5 times higher than its narrowest base dimension, it can become unstable in the wind. But Skytree's ratio is a daunting 9-to-1.
It's one thing to build tall and wide, and it's a much more challenging thing to build tall and slender.
So how do you build a super slim, record-breaking tower on such a confined plot of land? Engineers have always been able to build short and fat. And after a while, they mastered tall and fat. But building tall and thin has often been a problem.
Are you sure? Go for it.
Ireland's highest round tower is an amazing feat,
I told you, perfect.
but isn't exactly straight. The first St. Mark's Campanile in Venice certainly looked the part.
Mamma mia.
But the impact of the weather and the weight of its 5 mighty bells led to disaster.
We're going to need a newer tower.
Engineers had to return to the drawing board. During the 1920s, Chicago became synonymous with skyscrapers. By the 60s, with space increasingly at a premium, developers wanted to build even higher. But traditional, bulky construction methods were stifling their ambition. However, in 1968, engineer Fazlur Khan came up with a game-changing solution.
All right, thanks.
And architect Jayshree Shah is here to get a bird's-eye view of it.
This is the groundbreaking building that Khan was working on.
Over 1,100 feet high, the Hancock Center was the first skyscraper in Chicago to reach 100 floors. But this impressive building sits on a footprint 27% smaller than the city's second tallest skyscraper from that time, the Chase Tower. So, how does the Hancock Center continue to stand in the face of Chicago's legendary wind?
Just take a look at this skyscraper-shaped tower. If I push on it just a little bit, like a lateral force similar to the wind, you can see how much it bends. Now, if I push even more, you can see how it begins to twist. Oh, jeez. All right, I broke it.
But the simple addition of 45-degree cross braces changes everything.
You can see how much stiffer it is. When I push against the building now, it's not bending or twisting as it did before.
Called braced tubing, Khan used this technique to reduce the horizontal loads on the building. As the winds pushed against the building, their force now transferred down the diagonals to the base of the structure, easing the load on the building's vertical columns.
Fazlur Khan's brace tube design sparked a renaissance in skyscraper construction.
As well as defying the odds, its designers have also created a shape that makes Skytree totally unique.
The shape of this tower is characterized by the triangular shape at the foot and gradually transformed into circular shape to the top. That came from traditional Japanese architecture, so gentle curve, the maiden structure.
This is King Dakar, the tallest roller coaster in the world and the fastest in the USA.
I've worked on a lot of different rides, but I've never done a ride this big or this fast. This definitely topped them all.
With jet-like acceleration.
Arms down, head back, hold on.
And twice as high as the Statue of Liberty at 456 feet, this finely tuned construction is a perfect balance of science and engineering genius. Roller coaster engineer Michael Reitz is central to its construction.
You take it when loaded, a 22,000-pound train, and you launch it up to 128 miles an hour in 3.5 seconds. That in and of itself is an amazing feat. But then you're also putting it on this tower that's huge and supporting the track and the train. And then in the end, you're stopping it. You're taking all that energy back out. The engineering that goes into that is a pretty amazing feat.
Situated at Six Flags Amusement Park, this record-breaking roller coaster has another engineering trick up its sleeve. Built within the structure of the 456-foot Top Hat Tower is Zumanjaro Drop of Doom. The highest and fastest drop ride ever built.
I think a ride of this size and this complexity doesn't come around very often. It takes a lot of time, and it takes a lot of money, and it takes a lot of energy to create something this dramatic.
Opened in 2005, this 950-meter adrenaline-fueled ride has pushed roller coaster design to its limits. A 12,500 peak horsepower launch system fires trains from 0 to 128 miles per hour in just 3.5 seconds. After scaling the 456-foot tower, riders plunge into a three-quarter spiral, crest a second hill, completing the ride in just under a minute. And daring engineering has incorporated Zumanjaro, a 415-foot, 90 miles per hour, so-called Drop of Doom. With each rise and fall, twist and turn, the rider experiences a mixture of acceleration or gravitational forces, which form the foundation of the ride experience. But to design and build a ride of this nature means pushing engineering to match the limits of human endurance.
We're always looking for ways to top something that's been done before. We want to have the steepest drop, or the most inversions, or the tallest, or the fastest. But it's hard to innovate. I mean, physics are physics, and you know, you can only do so much to the human body.
So how do you push the boundaries and build the highest and one of the fastest rides in the world? This would not have been possible without the work of daring innovators of the past. American inventor Lamarcus Thompson was inspired by the gravity rides of the Pennsylvania Coal Railway. Opening his own version at Coney Island, New York, it was an instant success. But to stay ahead of the game, Thompson needed a new concept. And in 1887, introduced the Scenic Railway, a purpose-built ride that incorporated artificial scenery.
We're behind the scenes. We're so lucky we're actually walking on the track. Now, this is one of Thompson's original designs and is a huge leap forward from the Coney Island ride.
Thompson's American ride had purely taken passengers in a straight line. But his unprecedented Copenhagen creation takes a 625-meter figure-of-8 route, allowing passengers to get on and off at the same point. And his newfangled construction had another surprise innovation.
There's an electric motor that operates a chain lift that raises the passengers to the top of the 26-meter high hill you can see here behind me.
Once at the top, the laws of physics take over. As the cars roll down, gravity creates acceleration and kinetic energy, until the next hill forms potential energy. This pattern then repeats as the free-flowing roller coaster motion takes hold.
The route to Banna can reach speeds of up to 36 miles an hour. Now, because this ride relies on gravity alone, there's a brake person behind me. So if we get too fast, the brake person manually slows us down. Without that, there's a chance that the carriages might lift off the track.
With his breakthrough engineering, Thomson's scenic railways were in high demand. And by the end of 1888, his white-knuckle rides totaled 44 worldwide.
Thomson laid the foundation for the modern roller coaster. He was a genius of his time. And without his work, this wouldn't nearly be as much fun.
Back in New Jersey, design engineers have taken the basic principle of Thomson's gravity railway and supersized it, creating a record-breaking ride. By accessing the platform near the ride's 456-meter summit, it's clear just how far roller coaster engineering has come.
I'm not sure if we started with the idea of building the tallest ride in the world or if we started with building the fastest ride in the world. But essentially, those two things have the ability to go hand in hand.
Constructed from 1,400 tons of tubular steel and over 40,000 metal bolts, this truss frame construction is a modern engineering masterpiece. But like Thomson's scenic railway, it relies on a mixture of momentum and gravity to turn potential energy into kinetic energy. A ride of this scale, however, means rewriting the roller coaster rules. And today, Michael has the park to himself to put the ride through its paces.
Oh my God!
Known as an accelerator coaster, the kinetic energy needed is generated on launch. Once underway, the success of the ride relies on its design.
Wow, we are up at the top already!
Speed, height, and length of track is precisely calculated to complete the circuit. But crucially for passengers, the speed is converted into a ride experience that can be tolerated.
This misconception that people have of height and speed relating to G-forces, it's really only related to the accelerations. And as long as we stay within the accelerations that have been established and what the body is capable of handling, then we can go taller, we can go faster. That ride is intense every time.
It's a hostile environment and it presents a major challenge for any kind of engineering construction.
But this is an unprecedented engineering marvel. The London Array.
London Array is the world's largest offshore wind farm.
175 towering turbines capture the energy of the wind and convert it into record-breaking levels of electricity.
On an average year, the wind farm produces over 2 billion units of electricity. That's enough to power 500,000 UK houses.
Captain Nick Coville is part of the team making this immense wind farm a reality.
To give you some idea of how epic this is, the area of London Array is a greater surface area than the city of Manchester.
It's an army of giant spinning windmills that cover more than 100 square kilometres.
Right now, we're about 87 metres above sea level. You can see the rotor behind us, so each blade length is 58 metres. Standing out on these machines, it really does make you feel what a unique place to be.
London Array's turbines reach almost 150 metres above sea level. Each blade is almost as long as a jumbo jet's wingspan. Embedded in 650-ton foundations, they feed into 200 kilometres of cabling. 2 offshore substations send all this power to the mainland, where it provides enough electricity for 500,000 homes. But engineering on this scale at sea has never been done before. And this unpredictable environment throws up huge construction challenges.
It was a really ambitious plan to build a wind farm here. It's quite tidal restricted. There's a lot of change in tidal height, so there's very high currents, a lot of moving sandbanks.
The brutal marine environment also takes its toll on any technology.
If a piece of equipment fails, we're working to a very, very small weather window. We can't nip to the local hardware store and get another one.
But above all, in the middle of one of Europe's most extreme locations, these turbines must somehow generate year-round power on an unparalleled scale.
We need to generate electricity 24 hours a day, 7 days a week, in this remote offshore location. It's an unforgiving and unpredictable environment.
Out here, the challenges are enormous. But the team must do whatever they can to keep the blades turning. So how is it even possible to harness the power of the wind? Dr. Andrew Steele is on the windswept coastline of Scotland, searching for the relics of an idea that sparked an engineering revolution.
This 18th century salt mill is one of Scotland's best preserved windmills. The principle behind a windmill is simple. By taking linear motion from the wind, spinning those giant sails and creating a rotary motion, you can then use axles and gears to take that motion to wherever you want to use the energy.
This windmill would have once had large sails. Its rotation was used to pump seawater onto the land for the production of salt. It was a technology that hadn't changed for thousands of years. Just like today's engineers at the London Array offshore wind farm, Scottish engineer James Blythe was determined to generate electricity from wind power. And in 1887, in his back garden on the coast, he built the world's first wind turbine to power the lights in his cottage. But it's said his neighbours weren't impressed. They considered electricity the work of the devil. The energy from the turbine's blades can produce electricity in as little as 12 km/h winds. The turbine blades rotate an input shaft at up to 13 revolutions per minute. A gearbox makes the output shaft spin more than 100 times faster. A generator then converts this increased kinetic energy to electricity.
So the task we're given today is lubricating the main bearing. Those are like bearings in your car. Over time they wear out. The more we lubricate it, the longer it keeps going, the more power we can produce. This is what we're here to do at the end of the day. There we go. These machines, they don't stop. Summer, winter, Christmas Day. They've still got to run, we still need electricity.
Constructing just one of these mega structures is a huge engineering challenge. So how do you make 175 of them when your building site is the North Sea?
Not only do you have challenging seabed conditions, you also have different depths. It's a challenge from start to finish.
These 175 turbines make up the world's largest offshore wind farm, the London Array. For Head of Operations Graham Dawes, it's a perfect location for a bumper harvest.
Around the coast of the UK, we have more wind energy than pretty much the whole of the rest of Europe.
Spanning an area of 100 square kilometres. These 150-metre-high turbines are kept operational 24 hours a day, 7 days a week, to produce 2.5 billion units of electricity a year. Each of these massive marvels is made up of mammoth components.
The tower itself in two parts weigh around about 200 tonnes each. 3 blades per turbine. Each one of those blades is around about 25 or 30 tonnes each. And then the cell, the part that goes onto the top of the wind turbine, these can be up to 300 tonnes.
But constructing this army of giants in the unforgiving North Sea is the biggest battle of all.
The weather conditions can be very variable. We can have mist and fog as we have today. You can have nice flat calm seas, and you can also have storm force conditions rolling in without warning. Constructing the wind farm is a challenge.
It's a significant operation to install one of these turbines. Fast flowing tides, the nature of the seabed is extremely variable, so even in one location we could get a difference of up to 10 meters. The change is very, very extreme in a very, very small area. It's a challenge from start to finish.
So how is it possible to create a stable structure when your building site is underwater?
When I first saw it, I thought, wow, this is not something you see every day. This is really neat. This is really going out on the ordinary and really trying to do something that's different.
The construction process starts with the piece of land the Independent will eventually sit on. Measuring just over 1.7 acres, it massively constrains the size of the building that can be placed on top of it.
The parcel that we're allotted for this building is relatively, it's not a very large parcel.
Forcing Chris and the team to work hard to find a way to get the most floor space for their building.
The most area we could get was to create this square. So that was probably not the best shape that we could have come up with. The reason why the square shape was not good structurally was that the square shape in a skinny building created the largest projection area for wind to hit it. As anybody knows, you can get a windy day and big wind gusts. They blow stuff away. You have lawn furniture and it flies over. So those same forces hit this building, but on a much larger scale. And when they hit this building on the side that's projected against the wind, that produces a force laterally that we have to resist back down to the foundation.
To overcome these forces, Chris and his team designed the building around a central core that contains the elevator shafts, staircases, and maintenance rooms.
The building core, another way to put it, might be the central spine of the building. It's providing the primary lateral backbone resistance. The core on this building is made from cast-in-place concrete. What concrete does very well, it's an excellent material used in compression. However, it doesn't work very well in tension. Unless you have something else, it's going to lose its strength very rapidly. And that would be definitely something we do not want to see in a very tall building.
To ensure their core doesn't simply crack and fall apart, engineers must look to the pioneering innovators of the past. In the US city of Cincinnati, engineer Dan Dickrell is discovering the secrets behind a long-forgotten building that fundamentally changed the way we build tall structures.
So when you think about the history of tall buildings, Cincinnati is not exactly the first place that comes to mind. But this building right here is historic and important, just as much as those famous and iconic buildings in New York and Chicago.
Completed in 1903, the 16-story Ingalls building used old materials in a new way that was revolutionary for its time.
It's been empty for years, currently under renovation. Now, when it was built, it was the tallest concrete frame structure in the world. No one had built anything as half as tall out of concrete before because concrete itself was kind of a problem.
Luckily for the engineers constructing the Ingalls building, one man was working on an ingenious solution. English engineer Ernest Ransome moved to the United States in the 1870s, whereupon he patented a method for reinforcing concrete that would radically transform construction techniques worldwide.
All right, so what Ransome came up with is up here at the top of this ladder. We can see a piece of it. I'm gonna pull it down. This is rebar, so it's a steel rod that gets placed inside the concrete. The concrete and the steel work as a team. The concrete takes the compressive forces and the steel takes the tensile forces in bending and enables this magnificent structure to exist in the way that it does. Ransome's contribution to steel reinforced concrete was this fluted structure, or the spiral. Now what this does is when this rebar is placed inside the concrete, it increases the adhesion or stickiness between the steel and the concrete. It's effectively the skeleton of this building where the concrete would be the body.
To find out just how much of a difference Ransom's discovery makes versus concrete alone, Dan has traveled to an advanced materials testing laboratory.
This 4-point bend test machine is going to subject these pieces of concrete just like an overhead beam would be, in terms of the top will be compressed and the bottom will be stretched or extended. The bottom region is where the maximum tensile forces are going to be, and that's where we should see cracks.
First to undergo the test is the standard concrete block.
So I'm going to slowly increase the load here. What we have here is a readout that's showing the peak load that's currently inside this concrete block, and that number is going up and up and up as this machine presses harder and harder into this block. And so right now we're at 1,500 pounds of force inside the concrete block.
That's the equivalent weight of 1.5 grand pianos.
So it's a pretty strong material in and of itself, it's concrete, but at some point it's just going to have to give up. And let go. Our non-reinforced concrete broke at a peak force of just shy of 3,000 pounds. There was so much stress built up inside this concrete block that a crack formed right at the middle of the bottom surface, and it shot its way up through.
Up next, the steel reinforced concrete.
Those tensile stresses that are in there that rip the concrete apart are now basically living inside the pieces of steel. And that's the magic of steel reinforced concrete. When it goes, it's going to go quick. And there we go. So the test with the steel reinforced concrete, the peak load was around 7,700 pounds. That was substantially larger than the non-reinforced version. So we can see the effects of putting steel inside is quite substantial and impressive.
Able to sustain more than double the load than concrete alone, Ransom's invention was a game-changing material, allowing architects and engineers to redefine what concrete was capable of. Jutting out from the swarming skyline is an entirely new type of superstructure. This is 111 West 57th Street. Not only one of the tallest residential towers in the world, but also the most slender building ever constructed.
Designing a building like this is a once-in-a-lifetime opportunity.
This is definitely one of the most complicated, if not the most complicated, residential build going on in the world right now.
What you don't see is all of the engineering feats that are behind the walls. You have all these different components that are tied together that are just incredible.
Protruding from the ground, this gravity-defying giant marks the dawn of a new age of skyscraper.
Takes about 7.5 minutes to get all the way up. It's a pretty nice ride.
Going all the way up, Tommy. Once you clear all the surrounding lower buildings, at this height, it's another planet, another world. This is the reason why we're building this.
At 85 stories above the ground, the construction hoist reaches its limit. To venture even higher, John must climb to the steel summit.
So right now we're standing higher than any of the viewing platforms in all of New York. When you're up at this elevation, you got 360-degree views of everything surrounding Manhattan. You got Central Park to the north, Statue of Liberty, the Freedom Tower. It really is just breathtaking. It's iconic and has the same type of feel that the Empire State Building had when it was being built.
111's daring construction team reach heights few have ever been to. They are the only people to have ever experienced the tower's unrivaled views over New York City.
Up here, we have ironworkers. They're bolting up, erecting the steel, which is pretty challenging up at 1,300 feet in the air, up to 1,400 feet. It's pretty intense. Every day, I'm blown away by the amount of engineering and time and planning it goes into putting this type of a building in place.
Partially built over the historic Steinway Concert Hall, 111 West 57th Street sits on an astonishingly small plot. The tiny 18-meter wide site bears New York's third tallest tower that reaches a staggering 435 meters into the air. With a width-to-height ratio of 1 to 24, it is the most slender tower on the planet. The tower is flanked to the east and west by huge concrete sheer walls, 383 meters tall, and capped by a 52-meter steel crown, making it the second tallest residential building in the Western Hemisphere.
It is immense. What an amazing structure. So impressive.
Opened in 1981 and measuring a staggering 315 meters in length, the mammoth six-span viaduct carries a single track across twin-legged piers, a vertigo-inducing 76 meters above the river.
Wow.
But to see what makes this bridge truly revolutionary, you need to look much closer to the ground.
When designing the South Ringatike Viaduct, engineers had to consider the earthquake conditions it needed to operate under to keep the critical North Island main trunk line functioning.
It was the groundbreaking work of eminent earthquake scientist and engineer Dr. Ivan Skinner which provided the answer.
At the time the Mangaweka deviation was being planned, seismic engineering technology was in its infancy. So the designers of the South Ringatike Viaduct had to come up with a completely new solution: base isolation.
The first of its kind in the world. The bridge's innovative design features energy-absorbing dampers in the foundations, which allow it to step from side to side when a tremor hits.
Okay, so we're just putting together a really basic demonstration to give you an idea about how base isolation works. To begin with, we've got a shake board, which is going to mimic the horizontal forces of an earthquake. Now, usually you'd build your bridge straight onto the earth. With the South Ringatike Viaduct, however, we've got the foundations, and then we've got the base isolation, then we've got the pier.
Unlike traditional bridges, the foundations consist of two sections. One built into the ground and the other fixed to the bottom of each pier. At the base of each pier sits a set of rubber pads, which act to absorb a portion of the energy created in the event of an earthquake.
So these tennis balls are standing in for the flexible bearings or pads that are in the base isolation. And this is a platform that the bridge pier is going to sit on. Okay, so now that we've got the foundations sorted out, we're going to build our piers. This is just a standard old bridge, build it straight into the ground, onto the foundations, and here is a pier from the South Ringatike Viaduct. But to show you the full effect of how the base isolation works, I've just got to duck off and get some water.
Rather than rigidly fixing the bridge, the base isolators effectively separate it from the ground for greater flexibility.
Okay, so here comes an earthquake. And as you can see, the one straight into the ground is absorbing all of the energy from the earthquake, so it's more likely to fail and the bridge collapse. While the South Ringatike Viaduct, it's not absorbing as much of the earthquake forces, so it's less likely to fail in the event of an earthquake.
Under most circumstances, the bearing pads absorb enough force to keep the bridge structurally intact. But in a major earthquake, the pier can lift up by as much as 13 centimeters, allowing it to step from one leg to the other, preventing a catastrophic collapse.
And that's the genius of base isolation.
Every day, Ivan Skinner's inspired innovation enables trains to traverse the length of New Zealand's rugged North Island, keeping the country moving even when experiencing the most terrifying tremors.
Engineers weren't going to let earthquakes stop the railway. This is an ingenious piece of engineering, and I love it.
Built from a central concrete core, the tower's unique hybrid superstructure is pulled up around it. 40 floors constructed of steel, 29 stories of concrete, topped off by a monumental 23-story spire at the pinnacle of the building. Building a tower this tall in the middle of London presents some unique logistical challenges.
When you're building a tower that's over 300 meters high, one of the real challenges is getting the people and the materials up to these incredible heights when you're doing the construction. And the higher the tower gets, the harder that challenge becomes.
Construction had never been attempted before at a building this tall in central London, and it was a real challenge to get men and materials up to the top floor.
So how do you get enormous amounts of building material to the top of a mega tower like the Shard? It would be impossible without help from the innovators of the past. To construct the Great Pyramids, the ancient Egyptians had to rely on elbow grease and a lot of determination to scale their network of ramps. As cranes were introduced, the tread wheel allowed engineers to use leg power with impressive results.
Faster, faster.
Only walking pace was recommended. Erecting a giant obelisk in 16th century Rome required even more muscle. It took 800 men to raise a vast lifting tower. Plenty of power to get it up, as long as no one let you down. A more reliable solution to heavyweight lifting came 3 centuries later. Dr. Rhys Morgan is exploring the waterways of Venice, soaking in a centuries-old seafaring tradition, which ultimately led to an engineering innovation.
Throughout history, this city has had an unshakable affiliation with all things waterborne, and the mid to late 19th century was no different. It was a time of great change in the maritime industry, and old wooden galleys propelled by oar and wind were being replaced by steel-hulled ships and great big engines.
This new wave of heavyweight ships posed a huge problem for engineers at Venice's historic naval shipyard, the Arsenal. Traditional manually operated cranes couldn't handle heavy loads. This seriously compromised the Italian Navy's boat building program. They turned to British engineer Sir William Armstrong. He came up with the perfect solution to Venice's maritime construction conundrum.
Because of the growing trend of metal hull construction, the Navy decided to commission just the thing for the Arsenale. And here it is. The stunning Armstrong crane.
Completed in 1885, this colossal structure is an imposing addition to the Venetian skyline. And today, Rhys has special access to its inner workings.
And the way it works is like this. This huge boiler would generate enormous amounts of steam, and that steam would flow up through the pipework down into these chambers below. The steam drove these enormous pistons back and forth, and they in turn helped pressurize the hydraulic circuit. The water was taken from the lagoon outside, and the pressure from the pistons generated huge amounts of pressure on the hydraulic system itself.
The Armstrong crane can lift what was, at the time, an unimaginable 160-ton load. It transformed the fortunes of Arsenal.
It was the power that meant that previously unimaginable weights could be lifted, and it opened up a whole new frontier in crane technology.
Over a 30-year period, 9 more of Armstrong's cranes were installed around the world, ushering in a new era in crane development. The Shanghai Tower. Over 2,000 feet tall, it's the second tallest building in the world, and the tallest ever built in a seismic zone. It's the most technologically advanced skyscraper on the planet, with 128 floors and 9 indoor gardens, where 16,000 people will work, sleep, and play. It truly is a city in the sky.
Building a super high-rise building in Shanghai is quite unique because you have to deal with the wind load and also the earthquake load.
For lead structural engineer Dennis Poon, the project was an exciting challenge.
I cannot believe that today we're designing the tallest building in China and also the second tallest building in the world.
The engineering challenges for the Shanghai Tower began at its foundations. Because not only is Shanghai in an active seismic and typhoon zone, it's also sinking. The land under this massive metropolis is deflating like a giant air mattress. Its shallow water table is collapsing under the weight of the city's modern buildings.
For the Shanghai Tower, one of the biggest challenge is the foundation to support this super tall building. With its weight of 850,000 tons, how do you support it in the soft soil condition, which is locally in Shanghai?
Solid bedrock is 650 feet down. Above the bedrock is a soft layer of sand, clay, and soil. Without a solution, the 850,000-ton Shanghai Tower would surely sink.
So we have to design and build this foundation for the tower to deal with these challenges.
The engineers only have one shot. There's no room for error when you're building a tower this tall.
For a super tower, of course, the whole design challenge is to do the foundation right, so you don't have future problems, because you can't fix it later.
A modern world full of skyscrapers was once inconceivable. Early man was limited by what nature provided. For the ancient Egyptians, taller meant wider, and an awful lot of manpower. Unless you believe in some of the more otherworldly theories. When it comes to building towers, the ground below has frequently thrown a wrench in the works.
Mamma mia!
In order to create a skyscraper 11 times taller than Pisa's famous Leaning Tower, the designers of the Shanghai Tower will need to draw inspiration from the work of a 19th century engineering pioneer. The Shanghai Tower is the most technologically advanced skyscraper in the world and the tallest building in China. The tower's tapered, notched V design maximizes its aerodynamic performance, making it one of the most wind-resistant skyscrapers on the planet. But the Shanghai Tower faces a natural force even more destructive than high winds: earthquakes.
Shanghai Tower is the second tallest building in the world. Of course, we're not only designing this building for typhoon wind load up to 120 miles per hour wind load, we also have to design it for significant and severe earthquake.
Shanghai is in a level 3 seismic zone. Building the Shanghai Tower strong enough to survive an earthquake will be a daunting task. Earthquakes can be some of the most devastating natural disasters on the planet, leveling buildings and triggering tsunamis. China's neighbor, Japan, is the most seismically active country on the planet. But for years, no one could understand why modern buildings would collapse in an earthquake while traditional pagodas stayed standing.
この五重塔、当時の五重塔は高さ51メートルですね。日本で一番高い五重塔です。それがこのように約400年間大きな地震、それから強い台風に耐えてきました。これ本当に素晴らしいことだと思います。
The secret to the pagoda's survival is hidden inside.
まず第一に非常に柔らかい構造ですよね。多くのジョイントがあって、それから食い物もありますし、柔らかい構造なんですね。ですから、地震が来ると、スネークダンス説というそういう説を唱えた先生もいますけれども、要するに蛇がこうね歩くように、そういうような例えで強度を示すことがありますけれども、くねくねとこう強度をする。
The typical pagoda consists of 5 floors. Its floors have the ability to move independently of each other. When an earthquake strikes, its snake-like pattern keeps the center of gravity more upright than a rigid building would. And the wooden joints that support each floor are made up of several separate components, so each part can slide and move. The friction the parts create acts like a damper to soften any movement.
接合部が多くの接合部がところでエネルギーをですね吸収するというシステムを持っているわけです。
Today's engineers will need to take the 5-floor pagoda's innovative earthquake-proof design and apply it to the 128-floor Shanghai Tower.
You can see we have a 1,200 tons of steel block being hung 4-story above us. We are walking to the upper portion of the TMD system, two-mass damper system. Without this two-mass damper, we have to use a lot more structural steel and material to stiffen up the building.
Despite taking up 5 floors and weighing over 1,000 tons, the Shanghai Tower's tuned mass damper actually makes the building cheaper and lighter to construct. It took 15 years of planning, design, and testing, and 7 years of construction to raise this super tower from its foundations deep in the Shanghai soil to the tip of its 128th floor, over 2,000 feet up.